Alright, so what we're doing here for this problem statement is we're dealing with the different kind of page replacement methods. We're dealing with matrices, so we're trying to see if they're the same, and if not, we're changing the offset of the data there. The ones we're dealing with are going to be our FIFO, first in, first out, OPR, optimal page replacement, LRU, which is our least recently used, and MFU, which is most frequently used. We're not going to deal with the OPR itself because there's no point in doing that. It's more of a foresight kind of thing, and we can't really see the future, so there's no point in actually doing that one. So, as we said, page replacement, it's just a way to make sure that our physical memory, like if it's limited, we can add other things to it. So the physical memory is going to be small, but we have a lot of processes that we need to deal with, process like methods inside there. So instead of loading the whole process into it, we only load certain parts of it in pages, and the pages get swapped out from virtual memory to physical memory when we need them. Because of this, we're going to be using the different kind of methods to kind of reduce the amount of page faults which happen when different pages are called. If they're not in the physical memory, it causes a page fault, which is very expensive. The assumptions for this problem are that we are going to be accessing random pages, or a random number of pages, we don't know, that they're going to be randomly accessed from different times. It's not going to be sequential. It's not going to be 0, 1, 2, 3 pages. It's going to be 0, 5, 1, 6, 12, that kind of thing. Page faults will occur if we don't have the pages in physical memory and they're just in virtual memory. And we do have a limited physical memory amount for these matrices comparisons. For the requirements, we're assuming that, or we want anything that's going to be a solution to this problem to be scalable to however many pages we need. It needs to create the least amount of page faults possible. It can handle random access, like we said earlier, and it does not have a large overhead. We want to have a small amount of memory, physical memory, used by this comparison as possible. So methodology, we're doing scalability as 10% of it. Page faults is 50% because it's going to be the most damaging to the actual system. It's going to make it slower and stuff if we have a lot of page faults. It can handle random access is 10% of it, and minimal overhead is going to be 30% because, like we said, we do have a limited memory, physical memory in the system. We don't want to use it all with our algorithm. We want to try to get as many pages as we can in there without needing to swap it out from virtual memory. So first in, first out is good with scalability because it is just you're using a list. So the way that you can do it is the head of the list is always going to be the same until you swap it. So no matter how many you add to the list, the head's not going to change. Least recently used is going to be a little bit more difficult because you need to you need to compare between the different pages to see which one is going to be taken out. Same with MFU, our most frequently used. It's going to be the same thing as our LRU, so those are going to be a little bit less than our first in, first out. In terms of page faults, FIFO is going to be okay because it's going to give the minimum amount of page faults if you're in if there's not a large amount of functions being used. Otherwise, it's not going to be so great. In terms of least recently used and most frequently used, least recently used will give less page faults than first in, first out because it's going to be cycling out the least recently used, hoping that the pages won't try to access the same memory again, like that it hasn't been used. So that way we're getting a worse or an easier amount of access to more frequently used things. In terms of MFU, it's the exact opposite. We're assuming that we're going to have less use of the same things over and over again, so we're cycling those ones out so we can get the ones that are going to be used instead in physical memory versus virtual memory. In terms of random access, we're going to be dealing with the same exact thing. FIFO is going to be a lot less. LRU is going to be a little bit better at it because it's going to be taking out things that are used less frequently so that we can get things that are more frequently used as in our pages. In terms of most frequently used, it does a bit better because we're assuming that random access means there's not actually a linear pattern to what's going to be used. We're not actually dealing with a certain amount of pages that are going to be, or a certain amount of methods that are going to be called a certain amount of times. So it deals with, if they're more frequently used, statistically they're more likely to not be used again. So that's why most frequently used being cycled out is better than our least frequently used, or least recently used. In terms of overhead, FIFO does take a linked list or something of that sort, so there's a bit of overhead there. LRU and MFU do not take linked lists. They're just dealing with an amount of bytes in an integer usually or something like that. So you're comparing those instead of having to do a list of things. It makes it a lot easier to deal with. In terms of that, LRU and MFU are very similar. In terms of the comparison for the matrices, MFU does seem a little bit better just because it's going to be able to deal with random access if the matrices are larger and can scale better. So that's the main reason we're going to be using MFU for this algorithm.